Okay, so welcome everyone to another session of the NCTS Algebraic Geometry Seminar. And today we are very happy to have Jie Liu from MASS in Beijing. And he will talk about Kawamata-Miyake type inequality for canonical Q-funnel varieties. Yeah, please.
So thank you. Thank you for the introduction and thank you for the invitation. I'm very happy to have our opportunity to give a talk in this very nice seminar to report my joint work with Haidong Liu from Sun Yat-sen University. So let me start. Okay, so let me emphasize that in my talk, I always consider varieties defined over the complex numbers, and the small n is always the dimension of x. So let me start with some motivations and then state my main results. So I start with some motivations. Also some. So in my talk, we are mainly interested in the so-called Q-funnel varieties. Let me give you the definition. So we start with an irreducible normal project variety. Project variety X. So it's called a Q-funnel if we have the following conditions. The first of all, we assume that X is Q factorial. That means every way divisors on X is in fact Q Cartier. Okay, Q factorial. Okay, and I also suppose that the minus X example, not canonical divisor. And the third one, I suppose that the big number of X is 1. Okay, so this is the definition of Q-funnel varieties. And why are we interested in them? First of all, I could give you a remark about them. First of all, according to the minimal model program, So for any projectile manifold X, okay, you are expected to find some birational contraction from X to a variety X prime. Okay, this is a birational contraction. Such that X prime is a minimal model. That means K prime is neuf. Okay, so in this case, X prime is a minimal model of X. Either you get a fiber space from X prime to Z, okay, which is called the Moiré fiber space. So here, Moiré fiber space just means that the relative anti-canonical bundle of X prime over Z is indeed ample. And also the relative Picard number of X prime over Z is 1. So in this point of view, Q-funnel varieties with mild singularity are indeed one of the outputs of the minimal model program. That means in the second case of Morel fiber space, you take Z to be a point. Then you get a Q-Fano lattice. Okay. So this is one of the reasons that we're interested in this kind of varieties. And for the second one is that according to the BAB theory, BBAV theory proved by Kocher-Birka. So Q-Fano varieties with mild singularity and indeed bounded with mild singularity. Bounded. So this just means if you fix the dimension of X, then you get only finite many deformation families of Q-Fano varieties. Here for mild singularity, basically you can take it to be epsilon LC or even a more simple one to be canonical one or terminal singularity or something similar. Okay. So in this point of view, we may have some hope to classify them, but of course, in high dimensional, this should be very complicated because even it's finite, but there are still many of them. Okay, so a very general problem is that is it possible to study the? I mean, there is a question we want to study the relations among numeric invariance, numeric invariance of Q-Fano varieties. Of course, with mild singularity. So now I can state our main theory, which can be viewed as some result in this direction. We studied the relations between the second chain class of the Q-Fano varieties and also the first chain class of it. So our first result, theory A. So this is joint work with Haidong Liu from Sun Yat-sen University. And we prove that if you take X to be a canonical Q-Fano varieties. So by canonical Q-Fano varieties, I mean it's a Q-Fano variety with a canonical singularity. Okay. And also we suppose that its dimension is at least 2. Okay. And also I suppose that it's smooth in codimension 2, sorry. Smooth in codimension 2. Okay. Then we prove that the first chain class indeed is bounded by its first, the second chain class of X is bounded by the first chain class of X. That means we have some inequality here. So the first chain class to power n is smaller than 4 times the second chain class of X times to the first chain class of X to power n minus 2. Okay. So here, this assumption here, so it's some technical problem to make sure that when we can use this to define, we need it to define the first second chain class, okay? To define this second chain class of X. Otherwise, if it has a singularity in codimension 2, so the definition of chain class may be more subtle, okay? So this is in any dimension, but if you look at the lower dimensional case, I mean, if we look at dimension 2 case, dimension 3 case, because for dimension 2, this is smooth. It's not interesting. We have classification in this case. If you look at the dimension 3 case, we get a beta bound. We get a beta bound. Let me state it arterial B. So you take X to be a terminal Q-final varieties, Q-final threefold. Then we can improve the constant 4 to be 3. Sorry, this to power 3. Okay. We can even do better. So if we assume in addition that the following index of x, q of x is bigger than or equal to 3, then the constant 3 can be even improved. We have some the C1 of x to power 3 is smaller than or equal to 1021 over 41 times C2 of x times C1 of x. And we can also describe the equality case with the equality if and only if x is isomorphic to the vector projective space P of 1, 2, 3, 5. Okay, so now let me explain you the notions of following index QQX here. So we use this notation of following index small q, big Q of x. So you start with the x to be any QT follow variety. Okay. Here by follow variety, I mean mass case is ample and it has except QT similarity. Then we define its follow index QQ of x to be a maximum of positive integer r such that minus x is q-linearly equivalent to r times a. Okay, here a is some ample weight divisor on x. Weight divisor on x. Okay, for example, we look at this vector projective space here. X to be the vector projective space P of 1, 2, 3, 5. Then we have QQ of x is equal to 11. Okay, here you can take the you can choose the weight divisor A to be the weight divisor defined by the cost, the first coordinate. Okay. Here x zero is the first coordinate of x. Okay, do you have any question about our main theories? Okay. If not, let me continue. I want to give you some remarks of the result. Okay. This kind of theories or problems intensively studied, okay, in the past decades. And I think the first result in this direction must be the very famous work of Bogomolov and Mielka, and also Yao, and later to the single case by Grab. Catechis, Peter and Touch. So in their case, we take X to be a projective variety such that X is large and big, and with QT singularity, then they prove that the first chain class, the second chain class of X, okay, and times the first chain class of X, no, not the second, not the first chain class of X, but X, okay, to the power n minus 2 is bigger than or equal to the first chain class of X times to power 2 times kx to power n minus 2. Now the coefficient, you can take it to be 2 times n plus 1 over n. Okay, n is the dimension of X. This is in general called the Bogomolov-Miaukhan-Yau inequality. Okay, so our theory can be viewed as some reverse version of this theory, because in their case, kx is positive. So in our case, minus kx is positive, so kx is negative. And in this minus kx positive case, I think the first result in this selection is obtained by Kawamata in 1992. Okay, he considered the case where X is the terminal Q follows threefold, and then he proved that in this case, the second chain class of X is also controlled by its first chain class. So he proved that you can find some constant B such that first chain class of X 2 power 3 is smaller than or equal to B times the second chain class of X times the first chain class of X. Here, but this constant B is not explicit, okay, in his paper, but later in a paper by Suzuki in 2004, he proves that, in fact, you can take this constant to be 288. Now, you can compare his result with ours. You can say that this is really a good improvement, because here it's 288, but in our case, you can take it to be 3, okay? And also in the last year, by Wai, Zhang, and also Haidong Liu, they proved the higher dimensional case, higher dimensional analog of Kawamata's theory. They proved that if minus kx is large and big, plus and x has epsilon LC singularity, then you can always find such a constant B. Okay, then they prove that the first chain class of x to power n is smaller than or equal to some constant Bn times the second chain class of x times to C1 of x to power n minus 2. Okay, here Bn is a constant depending on the dimension of x and also the singularity epsilon. Okay, so their proof of this theory, depending on the is based on the BBAB theory. BBAB theory.
So in this statement, do you assume Picard rank 1 as in the
No.
Or nothing?
No, for nothing. If I don't write a Q follow, no, I don't have something, anything on the Picard number. Okay. If I write a Q follow, so we always assume that it has Picard number 1. Okay. But the result is very general.
Thank you.
You're welcome. Any other questions? Okay. The first remark, in fact, in 2019, I also studied this problems, but for smooth case. So I studied smooth Q-follow varieties. So in this case, of course, as asked by Xueyong, I assume that exercise picker number 1 also. Okay. Then I also prove that you can find some effective B, such that the first chain class to power to n is smaller than or equal to B times the second chain class of x times to C1 of x to power n minus 2. Okay. Here B is a constant between 2 and 4, which depending on the follow index of x. Okay. But in most cases, this constant is very close to 2, but in some case, it's close to 4. Okay. In very special case, it's close to 4. In most cases, it's close to 2. So in the smooth case, the boundary in general is good. It's better than the single case. Okay. Any questions about this part? If not, let me continue. Now I want to explain our proof of this two theory. So let me give you some idea of the proof of theory A. So our starting point is the following Langes inequality. Let me state it in a theory, which is proved by Lange. We start with irreducible normal projective variety X, okay, which is smooth in codimension 2. In codimension 2, of course, with dimension is bigger than or equal to 2. And I take E to be a torsion-free sheaf of rank R over X. And I also take an ample divisor A on X. Ample divisor on X. Then we have the following inequality. The first term is delta of E times A to power n minus 2. And I also have the term which is R squared times mu A maximum minus mu A times mu A minus mu A minimum over A to power n. Okay, so this is positive, non-negative, sorry. So let me explain the notions in this inequality. First of all, which is the delta of E, which is defined to be 2 times R times C2 of E minus R minus 1 times C1 of E squared. Okay, this is also called the discriminant of E. Okay, so if you look at this inequality, and if you look at this correction term star, so if this correction term vanishes, so this just means your second chain class of E can be controlled by the first chain class of E, and in this case, the coefficient can be chosen to be 2r over r minus 1. Okay, of course, I need to take r to be at least 2. Okay, of C2 of E is positive, is greater than or equal to C1 of E squared. Okay, if this correction term equals to 0. But in general, this correction term is maybe positive. So we need to find some control of it. But before that, let me give you the definition of the notions. First of all, it's mu A, okay, which is indeed defined to be the slope of E with respect to A, and which is defined to be the first chain class of E times to n A to power n minus 1 over its rank R. Okay, this is mu A, and for mu A maximum, which is indeed the maximum slope of E with respect to A, which is defined to be the sweep or maximum of all the slopes of non-zero subsets of E. So I take it to be mu A, the maximum of mu A of F. So you take all the F to be non-zero subsets of E. Okay, indeed, it's you can write all as supreme, but it's maximum. Okay, in any case, and also similar for mu A minimal, which is defined to be the minimal slope of E with respect to A. By definition, it's equals to the minimal slope of all the non-zero function-free quotients of E. So I take it to be the minimum of mu A of Q. Here Q is the non-zero quotient, portion-free quotient of E. Okay, you look at this one. So the mu A minimal is smaller than or equal to mu A, and the mu A maximal is larger than or equal to mu A. Okay, so this term is always non-negative. Okay, so if you look at this inequality, if we want to get a better control of your C2 of E in terms of C1 of EX squared, so you need to control this correction term. So right now, we only need to, yes, we needed to find some upper bound and an upper bound of the correction term, upper bound of the correction term star. Okay, but in this case, mu A is always fixed, right? Because it's a slope of E, but for mu A maximum and mu A minimum, it's still unknown. So we need to find some bound for them. Okay, so then you are reduced to find some upper bound of mu A maximum, and also a lower bound of mu A minimum. Okay, right? So now let me explain how to do this. First of all, let me start with the lower bound, okay, which is simple. Lower bound of mu A minimum. We apply this to the tangent bound of X. Okay. This is already studied before by many mathematicians, and we state in theory. So in the smooth case, this is proved by Peter Nel, and then in the single case, this is essentially proved by Wenhao, and we state it explicit in our paper. So if you start with a projectuality with the minus case, nerve and peak, and also with the QT singularity, then the minimal slope of the tangent shift of x is always positive. Okay, here A is any ample divisor Rx. For A, any ample divisor. Ample divisor Rx. Okay, in this case, we get the null bound of mu A minimal of the tangent bound of X for a final varieties. We have also some interesting consequence for the upper bound of mu A maximum. You just take for any non-zero subshifts of Tx. Okay, you can take its saturation. Okay, you can take F tilde to be the saturation of F in Tx. Okay, that means if you take the quotient, okay, take the exact sequence of shifts of Tx to Tx over F, 0, then F tilde is something like this. So F is the subshift of F tilde. Okay, and then you take the quotient is in fact to be Tx over F modulo the torsion. Okay, get another. That just means that F tilde is the pre-image of the torsion part of this quotient shift. Okay, and then you also have the first chain class of F is smaller than or equal to the first chain class of F tilde. Okay, so you take this quotient of Q. Okay, so either Q is 0. If it's 0, so F tilde is Tx, right? But if it's non-zero, you get a torsion free quotient of the Tx, and by what result? Then C1 of Q is positive. Okay, if Q is non-zero. Okay, here by positivity I mean it's an intersecting number with ample divisor with respect to ample divisor A. Okay, but if you look at the first chain class of F tilde, so it's equal to C1 of Tx minus C1 of Q. Okay, so this is smaller than C1 of Tx. Okay, again, the inequality should be understood in the intersecting number case with respect to any ample divisor A. Okay. Now, this means if we look at the slope of this F, so it's smaller than or equal to the slope of F tilde. So it's smaller than or equal to C1 of Tx, C1 of X over 2 if its rank is at least 2. Okay, this is already pretty good. You can use this to give a pretty good upper bound of the mu AX. But the problem is that if the rank of F is equal to 1, then this inequality basically tells you nothing. It's possible that the C1 of F tilde is very close to C1 of X. Then you get a too big one. We still have an upper bound, but this upper bound is too bad. Okay, so now the problem is that how to find an upper bound for the one subshift of this. This is the third part. We need to find some upper bound of the maximal slope of Tx with respect to some ample divisor A. So according to this part, okay, we only need to consider the case where the rank of F is 1. Okay, so in our paper, we give such a bound of X for Q-Fano varieties with canonical singularity, not for any Fano variety, just for canonical Q-Fano varieties. We take X to be a canonical Q-Fano variety, of course, with dimension at least 2, and you take L to be a non-zero subshift of its Canyon shift Tx, a rank 1 subshift. Then we prove that the chain class of L is smaller than or equal to the chain class of X over 2. Okay, and this is also the only place where we need to suppose that X is a Q-Fano. Okay, only place we need to assume that X is Q-Fano. Okay. In the first 2 steps, it works for any Fano varieties with QT singularity. But in this step, we do need to suppose that X is Q-Fano and also has canonical singularities. This is very important for us. And in general, this is not true. Okay. I mean, I should write a remark here. In general, the propagation does not hold for QT Fano varieties. We do have examples that the first chain class of L is very close to the first chain class of X. Okay, the gap of between them can be very small, can be small as possible. Okay, if the dimension of X is very large or something like that. Now I want to give you an idea of the proof of this proposition, idea of the proof of the proposition. So first of all, without lose generality, we may suppose that the C1 of L is always positive. Okay, we may assume that this first chain class of L is always positive. Okay. Otherwise, if the C1 of X is non-positive, so this inequality is automatic because the C1 of X is positive because X is a Fano variety. So then, in this case, by result of Kampala and Pine, we can find a rational map from X to a normal projectuality Y, which is a rational P1 fibration. Rational P1 fibration. One fibration. So here just means Y, so it's irreducible normal projectuality with dimension n-1. And if you take a general fiber, if you take C to be a general fiber of F, then the normalization of C is P1. Okay, and moreover, what's the relation of this rational map with the subshift L? In fact, this is the curve. L is indeed the kernel of the tangent map of F. L is equal to the tangent map of this rational map L. Okay. This notion is not good because F is not well defined everywhere. So you need to take the kernel of this rational map in the locus where F is well defined, and then you get a non-bundle defined over a big open subset of X. Then you take the preforward of this non-bundle. Okay, to X you get some reflexive rank 1 shift X. So then it's L. Okay.
Oh, so you assume that the subshift L inside TX is saturated?
Yes, because otherwise you can always take the saturation. Okay, sorry.
Okay, thank you.
Sorry. I write down here. It's better to, yeah. And L is saturated. Otherwise, you can just take the saturation of L in TX, okay? Because as we point out above, so if you take the saturation, the chain class becomes bigger, okay? So you just need to get a control of L tilde. It's enough. Okay. Right now we have something good because then you can find some divisor. You can find some. I take the normalization G here. Then you can find some delta, which is a QV divisor, effective QV divisor on P1. Okay, such that we have something like minus KP1 plus delta, which is Q-linearly equivalent to the first chain class of L restriction to C or pull back by G. Okay. Here, how you can imagine this thing? Because you look at this one, L is just a kernel of the tangent map. So this just means P1 is tangent to L, right? In a big open subset. So if you look, if L, for example, if L is locally free, then you can write down it as something like its restriction to C give you a subshift of the tangent bound of C, which is TP1. Okay, then delta is just the zero locus of this map. But in general, be careful that L maybe not locally free, so it's just a Q-Cartier. So you may need to take some symmetrical power of L, and you take some symmetrical power of TC. Then you get such a delta And finally, you get something like a Q weight divisor P1. Okay, this is something a bit formal. Okay, the good thing is that we have some control of this data. This is the result by Arroyo and also De Huel in the study of the so-called Fano formation. Indeed, in this case, this just means L is a Fano formation. So in their result, they prove that for Fano formation, this just means the C1 of L is ample, should implies that this pair P1 and the delta is not KLT. Of course, the result of Arroyo and De Huel is much stronger. It's a stage in the context of Fano formulations. But for us, in our very special case, this just means this log pair P1 and delta is not QT. But for this pair, it's very easy to say that if it's not QT, then the degree of delta is at least 1. Okay, so if you look at this formula star, then you can say that it's just like C1 of L times C, which is equal to degree of minus KP1 minus delta, so it's equal to 2 minus degree of delta, so which is at most 1. Okay, in this case, we get a control of the degree of CL times C. On the other hand, we need to control the first chain class of L, also of X, sorry. So, but if you take S to be canonical, if X only has canonical singularity, it's a very basic exercise in algebraic geometry by using the negativity lemma to show that the first chain class of X times C, so it's smaller than or equals to minus X times C. Which is equal, times C, which is at least 2. Okay, but note that X has bigger number 1, so we just need to check the intersection number of X and of L with any curves X. So then you can say that C1 of L is smaller than or equal to C1 of X over 2, because its bigger number is X is 1. Okay, so here you say that X is canonical, and also X has bigger number 1 is very important. Otherwise, this one maybe not. The lower bound of this one maybe like 2, maybe it's smaller. And also, if it's not bigger number 1, we cannot conclude this, because you have many different polarization. So you need to check it for different polarization. Okay. So of course, a very basic question is that we may ask, how about higher bigger number case? How about X to be canonical Fano varieties? With a higher bigger number. Okay, I don't know. I don't have counterexample in high bigger number case, but just that our argument cannot apply to this case. I hope this is still true for high bigger number case. Okay, so if you're interested in it, you may try to work also in this direction, which sounds to be difficult. But you may need some other ideas. Okay, and even for smooth case, okay, I don't know. Even for smooth case, even for smooth Fano varieties, I don't know if you can find some explicit bound B for smooth Fano varieties with high bigger number. okay, of a higher peak number. Okay. Finally, let me give you mention something about the proof of the idea of the proof of theory B. So the proof of theory B is very technical. So I don't want to go into the details. I just want to mention something we have used in our proof. So first of all, if you take X to be a terminal, Q follows 3 folds. Then we have some control on the follow index of X. Okay, this is by Suzuki. And then also by Prokhorov. They have proved that the follow index of X belongs to the set 1 from 1 to 9, and then 11, 13, and also 17, and also 19. Okay. Now for each Q of X, okay, we can explicitly write down. We can explicitly write down the possibilities of mu A maximum of X. Okay. Sorry, of Tx. For example, we can show that. For example, in this case, we can show that. For example, Tx is indeed Tx is semi-stable. If its follow index is at most 3. Okay, just use the result put before, and then you can also then you can apply the so-called Orbifold-Riemann-Roch theory in dimension 3. Orbifold-Riemann-Roch theory, and then you run some computer program. You try to compute the numeric invariance of X. Then you get some possibilities as the following. First of all, we can show that the first 10 class 2 power 3 is smaller than 3 times C2 of X times C1 of X if the follow index of X is at most 3. And in the other case, if the C1 of X to power 3 is larger or equal to 121 over 41 times C2 of X times C1 of X, and QQ of X is larger than or equal to 3, then we have 3 possibilities. Either X is anamorphic to the Vector projective space 1, 2, 3, 5. Okay, this is already proved before by Prokhorov. And we have some other possibilities where QQ of X, to point B. The second possibility is that the follow index of X is equal to 4. And we also have some numeric, we also know the numeric invariance of X. Okay. For example, it's de Grey, We know that the dimension of the linear systems are X and so on. And the third possibility is that the Fowler index of X is equal to 5, and also plus numeric invariance of X. For example, in this case, we have the C1 of X to power 3 times C2, let me see, C2X times C1 to X. So this is equal to, in the index 4 case, this is equal to 3, and this is equal to 25 over 8. Okay, now what we need to do is that we show that the last two cases are important. And this is some very technical argument. In fact, we exclude the last two cases. By an ad hoc argument using the so-called Sarkisov link. Okay. This is the method developed by Prokhorov's before the method developed by Prokhorov's. Prokhorov's in 2010. Okay. So I don't want to go into the details of the proof. Okay, so let me stop here. Thank you.
Oh, thank you very much. So are there any questions?
Okay, so in your theorem B, is it possible to consider the K is Nefn-Big instead of Fano?
No, I don't think so, because in our proof, you say the most important part is to control the slope of the rank 1 subshift of Tx. So our argument only works in Picard number 1 case. So I mean, for high Picard number case, I don't know how to control the rank 1 subshifts of the tangent bundle. So basically, this is the same for these questions. Okay, so you need to, so if you can do it for weak follow or even follow for high Picard number, you should be able to do it also for follow latches, any follow latches of high Picard number. Okay. I mean, our proof also depends on this proposition, even in dimension 3.
Okay, thank you.
Only works for Picard number 1 case.
Mm-hmm.
And
yes,
also canonical similarity.
So are there more questions? Also, actually, I think your seminar time is until 5 p.m. So you still have 30 minutes, but feel free to, yeah, if you want to talk more, then yeah, so you're free to ask some.
No, I don't have any to talk about the proof of theory. It's too technical. Basically, I can give you some sketch, but it's very complicated. You need to do some very ugly arguments. It's not so interesting. I mean, this is some idea developed by Prokhorov's. In fact, so for terminals, Q-Fano Swift, or even for terminal Fano Swift, we have the so-called Orbiford Riemann-Roch theory. So we can compute, we can So for example, for x, here I take x here, and take its not Pika group. I mean, I take its class group of weight divisors to be something modular Q-linear equivalence, which is by our assumption, which is anamorphic to Z times A. It will be some ample divisor. Let me suppose that the sum is simple. For example, this has no torsion part for this class group. Assume that we have no torsion part in this class group, so it's indeed isomorphic to A times Z times A ample divisor. And then use the orbifold Riemann-Roch theory. You can compute the degree. Okay, you can also compute the C1, the 2x of x times A. You can also compute the dimension of the linear system of A, and also the singularities of A. Okay, because of x. Okay, and then you get some program SRP, so you can blow up some points P. Okay, you can blow up of P. You get some x tilde here, and then you run some MMP flips, and then you get some x prime. That means right down is S bar, and then you get some Fourier fiber space or birational contraction to some x height. Okay. This is sorry, this is F. So here we have two cases. We have some the Pika number of x tilde and x bar is equal to 2, and F. You have two cases for F. F is either F is a Moiré fiber space, or F is a birational contraction. So this implies x tilde is again Q-Fallow, terminal Q-Fallow. Okay, the idea of program morph is that use idea of program morph. Sorry. Of program morph. Okay, using the numeric invariance of x, you can you can get control. You can get restriction. Sorry, you get restrictions on the numeric invariance of x tilde. Not all the numerical invariance of x tilde. Many of the follow index of x tilde, x hat. So you get control on the follow index of x tilde, x hat. For example, I mean, in this case, okay. in the second case of this. So you can control the follow index of get filter x hat and also the dimension of some k a x hat. Okay, x hat is the generator of the class group of x hat. Okay, then using again the Orbiford Riemann-Roch theory, you get information, you get more information, you get more information about x hat. Okay, and then you go back to x itself, and you try to find some contradiction, and then try to find a contradiction. Okay, this is the idea of this method of Sakharov link developed by Prokhorov. But the argument is that in fact is very ad hoc. I mean, for each different numeric type of x, okay, for each possibility of x, you run this program and you do these things, but there's no general approach to tell you how to get a contradiction. Okay, for each case, you may need a different approach to get a contradiction. So I cannot explore details about this approach. So, for example, in our paper, even for this case, this is most difficult. In this case, we write about 10 pages to exclude it. So we have many different possibilities for x hat, maybe more than 10. And for each cases, we need to find an argument to say that this is impossible. So maybe that's very interesting. I mean, even for you, if you don't not want to work on this problems. Okay, so yeah, I think I should stop here.
Oh, thank you. So are there more questions?
So the Fano, so when the Fano index is smaller than 3, what is the problem in your argument?
The problem is that we get many possibilities of okay. So first of all, so if Q2 of x, for example, in your case, you want to continue with Fano index equals to 1 or 2. Okay, then we can again use the Orbiford Riemann-Roch theory to find out all the possible x, okay, or the possible numerical invariance of x. Numeric invariance of x. But the problem is that everything blows up in this case. For example, we get more than 20 possibilities here. Of course, I need to say that I want to find all the numeric invariance for C1 of x to power 3 is larger than or equal to 121 over 41 C2 of x times C1 of x. Okay, this is the largest one we can find in all the known example. So it's this bound attended by the vector projection space P of 1, 2, 3, 5. Okay, right. In this case, even with this bound, you still find 20 possibility, more than 20 possibilities for Farad index equals to 2, and more than 1,800 possibilities for Farad index equals to 1. So we don't have any general approach to exclude the possibilities. With the only method we know is the Kirchhoff link developed by Prokhorov Wolf, but in big number, for example, his method, the method of sorry, I want to the method of Prokhorov Wolf does not apply to the big index 1 case. Okay, so we don't know how to exclude it or to find some exact example. And even for the index 2 case, we have so many possibilities. And if you look at our proof, you say that just for one case, we need to write 10 pages. And for 20 possibilities, we don't want to write, for example, more than hundreds of pages. But finally, we may find that even in that, we cannot exclude all the possibilities. So this is just some, the method is just that our method is not so good. It cannot apply to the general case.
So when you say numerical invariance, what kind of invariance are included in your data that consists of C1 to the cube and basket?
And all the baskets of all the baskets, for example, all the baskets, all the dimensions of the linear systems, and anyway, I mean, you can find all the dimensions of AA and all the so-called baskets of X.
Mm-hmm. Yes. Okay.
Okay. You can find all the. Basically, you can compute everything for X numerically.
Yeah. Okay. I see.
Yeah. Yeah. The dimension. The argument for dimension 3 case is it's not so good. I mean, yeah, it's very ad hoc.
Are there more questions? So could I ask a question about chain classes? So
yes,
at the beginning, you say that you assume your varieties are smooth in codimension 2 in order to define C2.
yes.
But so since we know that KLT singularities are so locally, there are quotient singularities in codimension 2.
Yes.
So would that be enough to define C2? So at least not the integral class, but the rational cycle.
Yes, yes, you can define the so-called orbifold the chain class.
Yes.
But the problem is that the problem I think is that the inequality we use in the inequality of Lange. I don't know if it can be generalized to the orbifold chain class, but in his paper, he just write down it for the usual chain class. So he also need to assume that the X is a smooth in codimension 2, but maybe with some efforts, you can generalize this to KLT singularities. But the problem, even in this case, I mean, I think the problem is that in the KLT case, you cannot get a control on the upper bound of the slope of the 10 class of rank 1 subshifts, because you look at our proof, we need X to be canonical. Otherwise, this bound in general is not true. Okay. I mean, if the singularity of X is QLT, so the C1 of L may be very close to C1 of X. So this estimate is not true.
But the bound makes sense when the singularity is canonical, but without the assumption that it's smooth in condemnation.
Yeah, but yeah, it's possible. But we just want to make everything simple. We don't want to go into some technical problems. I think it's possible. It's possible to do something like this. Yeah, if you get the right definition of C2 of X, I think this is almost tautological.
I see. So you think that Langer's theorem can be also holds for without this assumption, or just KLT? Yeah, KLT.
Yes, but I think maybe there are some problems that you need to consider some, torsion-free shifts, maybe not smooth. But in general, I don't know any good, any reasonable works in this direction for the Bogomolov or Mialka inequalities about torsion-free shifts on QLT similarities, on QLT varieties. But for the at least for the tangent shift, I think so. I think you can find many works in this direction. So at least in the theory of Langer, at least for E to be the tangent shift of X and X to be QLT, I think you can find something similar. Yeah, you just replace the second chain class of E by the orbit for the second chain class of E. I think it's true. I never find an explicit reference for this, but I think this can be done in some cases. Yeah.
Okay, so thank you very much. Are there more questions? If there's no more question, then let's thanks Liu Jing again for the very interesting talk. So thank you very much.
Yeah, thank you very much.